This is a recording of AP Calculus Chapter 1, Section 2A. This will be the first day that we spend on this. The notes for this is titled Functions and Graphs. So all of the functions and graphs that you have looked at prior to AP Calculus are all going to be covered in this one section of this chapter. So it's a lot. Let's start with just a few definitions, and if you can highlight these as you go, I think it's great. A relation is a set of ordered pairs. The set of first entries of the ordered pairs is called the domain of the relation. The set of the second entries is called the range of the relation. So the first coordinate is called the domain, the second is called the range. Typically that's x and y, but it doesn't have to be. The points in the coordinate plane that correspond to the ordered pairs is called the graph of the relation. So keep that in mind. A function is a relation that assigns a single element of R to each element of D. That's the formal definition of a function. The vertical line test for a function: if every critical line in the xy plane intersects the graph of a relation in at most one point, then the relation is a function of x. Here are some tests for symmetry. Symmetry about the y-axis. If x and y is on the graph, then when you plug negative x in, you should get the same y value back out. That will give you symmetry about the y-axis. A good example of this is y equals x squared. If you plug negative x in for x, you get the same thing back out. The parabola y equals x squared that opens upward is symmetric about the y-axis. Okay? So I'll write down an example here for you. Y equals x squared. Symmetry about the x-axis. If xy is on the graph, then x comma negative y is on the graph. Remember, if something's symmetric about the x-axis, it cannot be a function. It has to be a graph that lies on its side like a sideways parabola. A good example of this one is x equals y squared. So a parabola that opens to the right or opens to the left and that is still symmetric about the y-axis. And then symmetry about the origin. If you plug negative x in and negative y in, you get the exact same thing back out. Here's a nice example for you. And again, a lot of things that are symmetric about the origin may not be functions either. So I'll give you one that is a function. Y equals x cubed. If you plug negative x in, negative x times negative x times negative x, you get negative y back out. But you could also get something like this. X squared plus y squared equals 1. That's symmetric about the origin. If I plug negative x in for x, I get the exact same thing back out. If I plug negative y in for y, I get the same thing back out. So this actually has all three types of symmetry. So keep that in mind. A function y equals f of x is said to be an even function if when you plug negative x in for x, you get the exact same function back out. Just like we talked about right here. If I plug negative x in for x, I get the same thing back out for every x in the function's domain. Okay? A function is said to be an odd function if when we plug negative x in, we get the exact same function back out, except a negative sign out front for every x in the domain. Composition of a function. Remember, a composition of a function is f circle g. That's how I'll say it, f circle g. But remember, f circle g of x is f of g of x. Remember, functions are machines. They take an input and produce an output. The input is x, so x goes into the g machine. It will kick out typically a value, could be an expression, and then that new output becomes the input into f to produce my final output. Remember that the domain of f circle g consists of those x for which g of x is in the domain of f of x. Okay? Absolute value of a function. The absolute value of a function y equals the absolute value of x is defined as a piecewise by this formula. This will often confuse students. They will say, I thought the absolute value always had to be positive. How can it be negative x? Remember, this just says, essentially here's what it says. You probably learned absolute value this way. If you plug a positive number in, leave it positive. If you plug a negative number in, make it positive. Well, how do we make it positive? Is it magic? Poof? It becomes positive? No. When we want to take a negative and make it positive in mathematics, we negate it. So really, here's how you want to think of absolute value functions. Yes, if I plug a number in here and it's going to produce a positive inside the absolute value bars, we don't have to do anything with it. So if x is greater than or equal to 0, that's going to produce positive numbers or 0. We don't have to do anything with it. But if I'm going to plug a negative number in here, in order to make it positive, I have to negate what I'm plugging in. So anytime the argument of an absolute value produces a negative number, we have to negate it to make it positive. So it's just a little change in how we're going to verbalize it. Instead of saying, when you take the absolute value of something, if it's positive, leave it alone. If it's negative, make it positive. We're just going to say, if it's negative, negate it. Because when you negate a negative, it becomes positive. And that's all this is defining for us. Why is this important? It's very, very important. Because there are no rules in calculus for absolute value functions. We need to think of them in this piecewise format and often write them in this piecewise format before we can perform calculus on that function. Okay, so keep that in mind. So a lot of what you're going to be doing and a lot of the worksheet is going to be graphing. I'm going to be perfectly honest. Are you going to have to graph a ton of stuff on the AP test? No. But the more you know how to evaluate, you're going to have to evaluate all of these types of functions at various points. And the more you know how they look and how they react, once we start performing calculus to these functions, it's going to make a lot more sense to you. So on this particular one, it's going to say find the domain and range of each function, support your answer with a graphing utility, graph the function. Always list any intercepts and or asymptotes. Now, I am not going to necessarily graph each one of these. You can type that in your graphing calculator. I do have a graphing calculator here that I will type in sometimes. But on these videos, I'm expecting that people know how to type that into their calculator and produce the same thing. I want to see, can you graph this without a calculator? Okay? So a lot of times I will not do the support part. What we do want to do is be able to pick good values for x that are going to produce nice values for y. So in this particular problem, the most interesting value of x is x equals 1. Because that makes the argument of this function 0. 1 minus 1 is 0. And the square root of 0 is 0. We can find the square root of 0. 0 plus 2 is 2. Is 2 a good number to plug in? Yeah. 2 minus 1 is 1. Square root of 1 is 1. 1 plus 2 is 3. What about plugging 3 in? Let's just plug 3 in. We don't want to plug 3 in. We don't want to get the square root of 2 back out. I don't want to plug 4 in. How about 5? That works. 5 minus 1 is 4. Square root of 4 is 2. 2 plus 2 is 4. And you should be able to pick the next good number that fits on this 10 by 10 graph. It's not going to be 6, 7, 8, even 9, but 10 would be the next one. And I want you to become proficient at selecting quality values for the input that produce nice values for the output. It's a great skill that you should have for evaluation purposes. 10 minus 1 is 9. Square root of 9 is 3. 2 plus 3 is 5. So if I plot these points, 1, 2. If I go to the right 1, up 2. If I go to the right 2, up 3. If I go to the right 5, up 4. Oops, 4. Okay? And if I go to the right 10, I'm going up 5. And I connect those. Oftentimes on tests, I will see students try to put a vertical asymptote on a radicals. Okay? An even root does not have a vertical asymptote. It has an endpoint. That is the endpoint of this graph. It's going to impact my domain. For chapter 1, I want you writing domain and range using set builder notation as well as interval notation. After chapter 1, you can pick inequality notation or interval notation. It doesn't matter. But I want to make sure that you know how to write and read both. So here it is, the domain of this particular function. In set builder notation, we put a brace for set. And we start by saying x is the element, that's a curved E, of any real number, a double-lined R. Now, are you going to see a lot of stuff written like this in your calculus class? No. But you're going to see a lot of this type of notation in upper-level math classes, particularly like abstract algebra and other courses. I want you to get used to the set builder notation. Then we put a line. This line means such that. And then we write the domain. What is the domain of this particular problem? Remember, if it's an even root, we have to set the argument greater than or equal to 0. Add the 1 to the other side. X has to be greater than or equal to 1. Close the brace. But I also want you to write it in interval notation. Remember, interval notation. If we have an equal to, it has to be bracketed. If we don't want to include the number, it's parenthesized. The smaller numbers on the left, the larger numbers on the right. Well, this one starts at 1, and then it can go to infinity. So that's how we write it. We go bracket 1, comma, infinity. Parentheses. Never ever bracket on infinity. Never. Okay? They also want us to state the range. In order to state the range, so we put an R there with a colon. We do it the same way. Set builder. Y is the element of any real number such that, in this case, the Y values are greater than or equal to 2. You have to be able to know how to graph it really to get the range, or you got to be able to think intuitively a little bit on some of the ranges. But in this one, we really have to look at this and see, oh yeah, this starts at this endpoint and goes up, so Y is greater than or equal to 2. Therefore, in interval notation, the smallest possible value is 2, but it can go to infinity. There it is. Let's see what else it asks for. Domain, range. Okay, support using a graphing utility. You're always going to do that on your own. Graph the function. There's a nice graph. List the points. I'm always going to have a chart and tell you to list points. Now, I won't know if you use your graphing calculator, but I will know this. I expect nice quality points out here. Okay? Are there any intercepts or asymptotes? This never crosses the x-axis. It never crosses the y-axis. There's no asymptotes. So we don't have anything to worry about in terms of that. Okay? Remember, to find an x-intercept, you always plug 0 for y. But if I subtract 2 to the other side, I cannot take the square root of a number and get negative 2. That's why there isn't any x-intercept. Likewise, in order to get a y-intercept, you plug 0 in for x. I cannot take the square root of negative 1. That's why there is no y-intercept. Next example. Rationals. Rationals often give students some of the most difficulty. Okay? And the reason is because of the asymptotes involved and some of the fractional work involved. So we're going to start by saying this. I'm going to start by listing down here the vertical asymptote and the horizontal asymptote. When we're looking for a vertical asymptote for a rational function, we want to know what value of x creates 0 in the denominator, as long as it's not a repeated factor. If I plug 2 in for x, I get 1 divided by 2. That's undefined. That's why my vertical asymptote is x equals 2. A vertical asymptote is always x equals a value. The horizontal asymptote here, there are going to be a set of rules about end model behavior, and we will cover this in more detail in Chapter 2. But for now, horizontal asymptotes, there's two that you should know right away. If the degree on top is less than the degree on the bottom, y equals 0 is always the horizontal asymptote. If the degree on top equals the degree on the bottom, if this was x over x minus 2, we would look at the coefficients of the highest degree terms. Whatever that ratio is, we would set y equal to that ratio. And we'll see some examples like that as we go along. I'm not going to put anything on a test or a quiz that we would not have talked about. So I am going to dot in these asymptotes right away. Vertical asymptote of x equals 2. So I can see that on my graph. That's one thing. When you're using your graphing calculator, you're not going to see the asymptotes dotted in. You could dot them in by using a feature on the calculator, but when you do the, just plug it in, you're not going to see it. Okay. I also think it is a lot easier if we do domain and range right away, because these are going to help us determine the domain and range. The domain of this particular function. X equals 2 is a vertical asymptote. I cannot plug 2 in. Therefore, the domain x is the element of all real numbers such that x cannot be 2. How do we write that in interval notation? It's a little tricky. Negative infinity. That's how I start on the far left. I write negative infinity, comma, 2 parentheses. I'm not including it. That's why I use parentheses. And then I use a u for in union with positive 2 to positive infinity. So essentially, it's going from negative 2 to 2, but look at, the 2 has been negative infinity to infinity, okay? But the 2 has been excluded because I have a parentheses here and a parentheses here. Otherwise, the domain's going from negative infinity to positive infinity. Okay? We're going to do the same thing with the range, if that's the horizontal asymptote. Now, it is possible to have a point on a horizontal asymptote, but we will never equal 0 here. Y will never equal 0 in this particular problem. Now, in order for y to equal 0, it's called an x-intercept. And if I want to find the x-intercept of this function, I'd plug 0 in for y. If I multiply that up, it doesn't work. I get 0 equals 1. There is no x-intercept. Therefore, we know that y cannot equal 0. The range. And we'll see it once we see the graph. We'll even see it better. The range. Y is the element of all real numbers such that y cannot be 0. Writing that in interval notation. Negative infinity to 0 in union with 0 to infinity. A lot of times I'll put a positive in front of that just so I know it's positive, but you don't have to. The positive doesn't have to be there, but the negative does on this end. Never parentheses on infinity, and we don't want to parenthesize 0 here because we want to exclude it from the range. These mean the exact same thing. On the first test, you're going to have to write them in both forms, so I know that you know how to read both of them and write them. But from after Chapter 1, you can use whichever one you prefer. But I am going to ask you to plot points as we graph this so that we understand how these work. And we're going to get more practice on this in Chapter 2 when we talk about limits. The most interesting value of x here is 2, but we can't plug it in. It's undefined. So I'm going to start just working to the right. If I plug 3 in, that works out well. I get 1. If I plug 4 in, I get 1/2. I could plug in 5 and get out 1/3. Well, let's take a look. If I plug 3 in, I get out 1. 4, I get 1/2. 5, I get 1. It looks like it's just getting closer and closer and closer to this horizontal asymptote. It's called a limit. We're going to find out what closer and closer means. But I also want to, what happens then if I plug in, what happens if I plug in 2.5, right? If I plug in 2 1/2 minus 2, that's a half. And 1 divided by 1/2, flip, I get 2. If I plugged in 2 and 1/4, I was even closer to the vertical asymptote. 2 1/4 minus 2 is 1/4. 1 over 1/4 is 4. So the closer I'm getting to this vertical asymptote, this thing is taken off to a larger and larger number. Let's see what's happening on the other side. Let's investigate what happens if I plug 1 in. Well, 1 minus 2 is negative 1. 1 divided by negative 1 is negative 1. Here it is. What happens if I plug in 0? I get negative 1/2. What happens if I plug in negative 1? I get negative 1/3. Negative 1/4, negative 1/5. It's just getting closer and closer and closer to that horizontal asymptote. And we're going to define an asymptote that way in Chapter 2. That's what happens. You get closer and closer and closer to a value as x goes to infinity or negative infinity. What happens if I plug in 1 1/2? And I want you to be able to think this way numerically without a calculator. 1 1/2 minus 2, that's negative 1/2. 1 over negative 1/2, negative 2. What if I plugged in 1 1/4? Because that's even closer. Well, let's do that again. Let's make it 1 3/4. It's even closer to 2. Or even better, we could even do 1 7/8. 1 7/8 minus 2 is negative 1/8. 1 over negative 1/8, negative 8. The closer I'm getting to this asymptote, the larger the value is getting in the negative direction. Rational functions are oftentimes some of the more difficult functions for students. But here it is. Okay? What about x-intercepts and y-intercepts? I think that's the last thing here. An x-intercept. Remember, an x-intercept can be found by plugging in 0 for y. But we talked about that. If I plug in 0 for y and multiply that up, there is none. So just because I ask for it doesn't mean it will have it. The y-intercept, plug in 0 for x. When I plug in 0 for x, I get negative 1/2. There's a nice y-intercept. Questions on that one? Okay. So we got a few more of these here. Problem C. Cube root. I want to do a cube root for you because I want to make sure I do an odd root. We already did an even root, but I want to make sure that I talk about this odd root. We can take the odd root of any number, positive or negative. So the nice part is the domain of this function is all real numbers. Here is the benefit of knowing set builder notation. You can write all real numbers like that. Or you could write out all real numbers for the domain. Do not do ARN. I've never seen it on the AP test. They are not going to assume that you mean all real numbers by that. Do not do that on the test in here. I've never seen that abbreviation in any book or anything on an AP test. Okay? Here's how you write it in set builder notation. Negative infinity to positive infinity. The range here is also going to be all real numbers, but you would have to graph it first to see it. I'm going to write it down so I don't forget to do it. And that would also be negative infinity to positive infinity. Okay? There are no vertical asymptotes for this situation. There's no endpoints even. Let's just plot some points and see how it goes. The most interesting value for x is 2, and I know Mr. Hearn has talked to you about this. And it's 2 because 2 makes this argument equal 0. The actual function itself is a cube root function that makes that argument 0. 2 minus 2 is 0. The cube root of 0 is 0. 0 plus 1 is 1. Now let's just pick some points, but we're going to be clever about the points that we pick. We do not want to get cube roots out. We don't want to get decimals out. But can I plug 1 into this? Yeah. 2 minus 1 is 1. The cube root of 1 is 1. 1 plus 1 is 2. But I don't want to plug 0 in. I don't want to plug negative 1 in. Negative 2, now let's go the other, let's see what happens if we go the other way. Are there other nice positive numbers that we can plug in? What about 3? 2 minus 3 is negative 1. Yeah, the cube root of negative 1 is negative 1. Plus 1 is 0. So that works. But those 3 points are not going to be enough. Think about it this way. I want to think of what number for x is going to give me a perfect cube underneath here. So a good number to plug in for x might be 10, because 8 is a perfect cube. If I plug 10 in, 2 minus 10 is negative 8. The cube root of negative 8 is negative 2. Negative 2 plus 1 is negative 1. What about the other direction then? Well, I want to produce a positive 8. So I got to think, well, 2 minus negative 6 will give me a positive 8. 2 minus negative 6 becomes 2 plus 6. It's 8. The cube root of 8 is 2. 2 and 1 is 3. Okay? So here's what this looks like. If I go to the right 2, I go up 1. If I go to the right 1, I go up 2. If I go to the right 3, I go up or down 0. That looks like it's a straight line. It is not a straight line. If I go to the right 10, I'm going down 1. If I go back 6, 1, 2, 3, 4, 5, 6, I go up 1, 2, 3. It's got to go through all of those points. I'm going to turn this sideways here just for a minute. And if I sketch that in, it looks like this. Okay. It is really a sideways cubic function, right? That's what it is. Okay. If you could picture it like this, you'd say, oh, that looks like a cubic function. This is a sideways cubic function. Okay? So there's the domain, the range. We've got x-intercepts, we've got y-intercepts. That's the only other thing that it really asks for. X-intercept, y-intercept. Now, some of these will not look all that pretty. But to find a y-intercept, you plug in 0 for x. If I plug in 0 for x, I get the cube root of 2. So there's really not much I can do except write 0, comma 1 plus the cube root of 2. We're going to leave it like this. We don't want to give the decimal answer. If we wanted the decimal answer, I'd have you do it in the calculator and use your 0 key in your calculator. X-intercept. We find an x-intercept by plugging in 0 for y. Okay? Now we really have already done this, right? Here it is. There's y, 0. It's 3, comma 0. But you could have plugged in 0 for y. Subtract 1. Cube both sides. And then solve for x. So you can solve it algebraically as well if you don't stumble upon it in your point plot process. You can always find an x-intercept by plugging 0 in for y and solving for x. You can always find a y-intercept by plugging in 0 for x and solving for y. There are no asymptotes in this problem. D is another rational function. Now the reason why I wanted to do D is because of the type of asymptote that we're going to get out here. Okay? So let's just start with this particular situation. If I talk about the domain of this particular problem, x cannot be 0. It creates a 0 in the denominator. So the domain, x is the element of all real numbers such that x, this means such that, x cannot be 0. And if I want to write that in interval notation, I would say negative infinity, comma 0, parentheses, in union with 0 to positive infinity. So essentially, from negative infinity to infinity, but we are excluding 0 in this manner. We just parenthesize both of these. That's how we exclude. Okay? That's how you do it in this particular problem. So if 0 makes the denominator equal 0, that means it creates a vertical asymptote. This is a vertical asymptote. Okay? So x equals 0 is a vertical asymptote. The horizontal asymptote here gets a little tricky. Horizontal asymptote, I'll just abbreviate it there. I'll always have it spelled out for you most of the time on tests and quizzes. Really, it's going to be easier to see if we point plot this and kind of see what's going on, right? I can't plug 0 in, but can I plug 1 in? And this is why I love the point plotting process. I will go ahead and plug in or dot in this x equals 0 for my vertical asymptote. But a lot of times you think, well, the horizontal asymptote, oh, it's always y equals 0. Not the case, right? We might see something a little bit different here. All right. So in this particular situation, I cannot plug in 0. So I'll try 1. If I plug 1 in, 1 squared is 1. 2 minus 1 is 1. If I plug 2 in, if I plug 2 in, I get 2 minus 1/4. If I have 2 pies and I eat 1/4 of a pie, I have 1 3/4 pies left, right? You can get a common denominator and subtract, and you just think about it logically. If I plug 3 in, think about what's going to happen. I'm not even going to write it down. If I plug 3 in, I get 1/8. 2 minus 1/8 is 1 7/8. So maybe I'll write this down. What's going on here? Well, if I plug 4 in, I get 1/16. I'm going to get 1 15/16. I'm getting closer and closer and closer to 2, it looks like. So if I plug 1 in, I get 1 out. If I plug 2 in, I get 1 3/4 out. If I plug 3 in, I get 1 7. It's getting closer and closer and closer to 2. That means it's a horizontal asymptote. So y equals 2 is going to be a horizontal asymptote. So what happens if we get closer to the vertical asymptote? What happens if I plug a half in? Watch, this is the one I really like. If you plug a half in, you get 1/4. 1 over 1/4 is 4. 2 minus 4 is negative 2. So as I get closer to this asymptote, I'm going down here. That's what it looks like. You mean if I get really close there, I plug in 1/4. It's going to be a large negative number. Let's see. 1/4 squared is 1/16. 1 over 1/16. 16. 2 minus 16 is negative 14. There it is. What's happening on the other side of this asymptote? Well, that's kind of interesting. Well, look what happens on this one. If I plug in negative 1 and square it, I get the exact same thing back out. It's called an even function. It's symmetric about this y-axis. When I square it, I still get positive 1 out. As a matter of fact, if I plug in negative 2, I'll get this. Negative 3, I'll get this. So the best way to list these when you have this situation is you get a 2-for-1 special. Plus or minus, plus or minus, plus or minus. I don't even have to list this separately. Whenever we have a 2-for-1 special, meaning it doesn't matter if I plug in the positive or the negative value, you can just put the plus or minus out front. I'm going to get the same mirrored look on this side. Okay, so I'll plot a couple of these points. But notice, here is my horizontal asymptote. I'm actually going to use a marker so you can see it really well. Here is my horizontal asymptote. There it is. Now we're going to work extensively with these rational functions in Chapter 2. But the more that you can graph these now without the use of a calculator, the better off you're going to be. And you're going to have to know how these react. Notice that with this vertical asymptote, we don't get this changed look like we had on the previous problem when it was a 1 over x minus 2. Okay? Now we get this, what I call is a volcano look. So I'm going to want you to know the difference between a pole and a volcano. I did not make these words up. I will say it over and over again. I want you to be able to express the difference. This is a pole. You have to climb the pole and slide back down before you start the graph again. Or if you go down the pole, you got to climb it before you then come down again. That's a pole. This is a volcano. Now this is an upside down volcano. Goes down, you jump across as it starts. How do we tell the difference between this look and this look? Hopefully I can get by with just verbalizing this one time. This is going to help you immensely in Chapter 2 if you can get this down right now. If the vertical asymptote comes from a factor raised to an even power, this could be 2, this could be 4, this could be 6, you're always going to get this volcano look. Now it could open upward or open down depending on whether it's a subtraction or addition. But you're always going to get this jump across the asymptote look. If the vertical asymptote comes from a power raised, from a factor raised to the first power or any odd power, this could be x minus 2 to the third power, and this asymptote would be the same. You get this pole. This is called a pole. I didn't make these up. I stole it from some book. Not this book, but a different book. And it's a nice way to keep those straight, because I'll always ask you, is it a pole or is it a volcano? How do you identify? It's the same thing as x-intercepts. You need to know the difference between an x-intercept being a touch or an x-intercept being a cross-through. A perfect example is if you think of y equals x squared. The x-intercept comes at x equals 0, but it touches the point 0, 0 and goes back. That's a touch because the x-intercept comes from a factor raised to an even power. Where if it's a cross-through, y equals x or y equals x cubed, still has an x-intercept at 0, 0. But now it's x to the first power or x to the third power. If the x-intercept comes from a factor raised to an odd power, then it crosses through the line and passes through. Okay? It crosses through. Think of those two graphs. Okay? And I will ask you about those a lot. Let's talk about the range. Notice what happens with the range here and why we needed to graph it before I wrote it down. Because this range, all the values are below 2. So y is the element of all real numbers such that y is less than 2. How do we write that in interval notation? The smallest value is 2. The largest number can go all the way to infinity. If this could equal, it does not hit this asymptote, okay? But if it could equal 2, then we put an equal there, and this would be bracketed. But we never get a y value of 2 out. Ooh, and this range is incorrect, right? Right here. It's correct here. Y is less than 2. So I just did this to make sure that everybody was with me. If it's less than 2, the smallest possible value is negative infinity. Sorry about that. And the largest possible value is positive 2. Big difference. Same thing though, if this is an equal to, then I could bracket this. But the smallest value is negative infinity to 2. Last part of this problem, x-intercept and y-intercepts. Find an x-intercept, plug in 0 for y. Watch what happens. This one here, you pretty much have to do it algebraically. If I plug in 0 for y, I can add this to the other side. I can write 1 over x squared equals 2. How do I solve this? Well, multiply both sides by x squared. Divide both sides by 2. Take the square root. When I take the square root of both sides, I got to do plus or minus. So x is going to equal plus or minus, the square root of 1 is 1 over the square root of 2. Now, I want you to know, if it's numerical, we will rationalize. Multiply by the square root of 2 over the square root of 2. And I'm going to write it like that. It's 2x-intercepts, but I can write them both at the same time. Square root of 2 over 2, comma, 0. If you left it unrationalized, I'm not going to get worked up about that. I just want you to know how to rationalize because it's going to happen some. Some of the work is already done and you're going to see it rationalized. You do not have to rationalize on the AP test, and even the multiple choice problems anymore, they tend to de-emphasize the rationalization of it. Okay? To find a y-intercept, plug 0 in for x. I plug 0 in for x, can't do it. So it's none. 0 in for x doesn't work here. Okay? The last part of A is determining whether a function is even or odd. In order to determine whether a function is even or odd, or neither, most functions are going to be neither, right? It's kind of a unique function if it's even or odd. But what you want to do is you want to plug negative x in for x. If you get the exact same thing back out, it's even. If you get the exact same thing, but off by a negative sign, it's odd. In all honesty, it's easier just to plug numbers in. In other words, if I plug 1 in here, I get out 1 for y. If I plug in negative 1, I get negative 1 for y. If I plug 2 in for x, I get out 8. Negative 2 for x, I get out negative 8. If you get the same value but opposite signs, opposite goes with odd. Opposite, odd. Okay? O. This is an odd function. Okay? Here, if I plug 1 in for x, I get out 3. If I plug in negative 1 for x, I get out 1. There's no relationship. I didn't get the same thing back out, so it's not even. I didn't get the same thing but the opposite sign back out, so it's not odd. It's neither. And don't be surprised when the answer is neither. Most functions are neither odd nor even. But look, if I plug 1 in here, I get out negative 2. If I plug in negative 1, I get out negative 2. But don't always check a couple different numbers. If I plug 2, I get out 1. Negative 2, I get out 1. This is even. What about here? See, look what happens. If I plug in 1, I get out undefined. If I plug in negative 1, I get out undefined. If I plug in 2, I get out 1/3. If I plug in negative 2, I get out 1/3. If I plug in 3, I get out 1/8. Negative 3, I get out 1/8. If you plug opposite values in and get the same value back out, it's even. And I think it's easier to just think about them numerically. But think about this one. If I plug in 1, they're both undefined. So that doesn't tell me a whole lot. If I plug in 2, look what happens. I get 2 over 3. I get out 2/3. If I plug in negative 2, I get negative 2 over. I get negative 2/3. What happens if I plug in 3? If I plug in 3, I get 3/8. If I plug in negative 3, I get out negative 3/8. Opposite signs go in, opposite values come out. It's odd. Okay? Questions on that one? I think it's easier just to think numerically. Because a lot of students will look at this and say neither. It's got an odd term, it's got an even term, therefore it is neither. That only works for polynomial functions when you're looking at each term separately. It does not work for these rational situations. So just think numerically. Okay? This problem here, I just want to do these two for you. We're talking about symmetry, but notice if I plug negative x in for x, I get the same thing back out. If I plug in negative y for y, I get the same thing back out. If I plug in negative x and negative y and get the same thing back out, that means it's got all three symmetries. This has x-axis symmetry. It has y-axis symmetry. And it has origin symmetry. I ask you to graph this quickly just because I want you to be able to think about these a little bit here. If I divide both sides by x squared to get y by itself, watch what happens if I take the square root of both sides. I really get y equals plus or minus 1 over x. I get two different functions out. This is not a function. Anytime y is raised to an even power, it's not a function. If y is raised to an even power, it's not a function. It's a relation. It does not pass the vertical line test. So let's look at this as if it were two different functions. Can we graph this? Yeah. Notice, this has a vertical asymptote at x equals 0. Because that makes a 0 in the denominator. It has a horizontal asymptote of y equals 0. What is going on? Because the degree on top is less than the degree on the bottom. So what's going on? Well, if I plug in 1 into this, and this is the next here. If I plug in 1 into this, I get 1 out. 2, I get 1/2 out. 3, I get, look at it, it's getting closer and closer and closer to this horizontal asymptote. If I plug 1/2 in, 1 over 1/2, I get 2 out. It's getting closer and closer and closer to that vertical asymptote. As I get closer and closer and closer to this vertical asymptote, the values are getting larger and larger. What happens if I plug in -1? I get this out. -2 is -1/2. Well, look at it. I get this. It looks like this. You can plot some points, what it's going to look like. Notice, this vertical asymptote is a pole. If you know the difference between a pole and a volcano, it comes from a factor raised to an odd power. That's why you have to slide before you start again. Well, that looks like a function. It is. That is a function. But now let's graph this one. And I'll graph this one in pen here. If I plug 1 in, I get out -1. If I plug 2 in, I get out -1/2. 3, I get, it looks like this. And I'm going to get the same look here. What happens when I plug in -1? I get out +1. There it is. It does not pass the vertical line test. It does not pass the horizontal line test. Right? If we're looking for a one-to-one function. Okay, this is not a function. But there's what it looks like. It's a nice picture. It's a relation. We can graph it. It's just really made up of two separate functions. That's it. That's that. Okay? Watch what happens with B. If I plug in -x for x, I get the same thing back out. If I plug in -y for y, I get the same thing back out. This has all three symmetries as well. It has x-axis, y-axis, and the origin. Don't expect them all to be like this. These are just these two. The reason why I put this one is I want to make sure that you do remember how to graph ellipses and hyperbolas. This is an ellipse. If both these coefficients were the same, it would be a circle. If this was a 4 here, I could divide everything by 4 and get x squared plus y squared equals 9. The radius would be 3. But since I have different coefficients and a plus sign, it's an ellipse. If this plus sign was a minus sign, it would be a hyperbola. And this is at the end of pre-calculus. So there's a good chance you were in remote last year. But that's how it works. How are we going to graph this? Divide everything by this number here. You always want it set equal to 1. So when I rewrite this in standard form, it's going to be x squared over 36. If I divide by 36, I get y squared over 9. 36 divided by 36 is 1. So what happens here? Well, the center is 0, 0. That's the center of my ellipse. It's not a point on the ellipse. It's just the center. It's the opposite of whatever you're doing to x, the opposite of whatever you're doing to y. The larger number is going to tell us about what is called the major axis. The square root of 36 is 6. That means I'm going to go to the right 6 units. 1, 2, 3, 4, 5, 6. I'm going to go back. 1, 2, 3, 4, 5, 6. That is called the major axis. It's 12 units long. The square root of the smaller number is 3. And it's underneath the y. That's why I'm going to go up 3 and down 3 to find the endpoints of my minor axis. And I'm just going to sketch this nice ellipse in. Now, I don't know how much practice you had on this. It's not going to be a huge skill that's going to come up frequently, but you need to be able to recognize an ellipse versus a hyperbola versus a circle. And we're going to see lots of it, so no need to panic, but that's what that one would look like. Okay? That's the end of the notes for Chapter 1, Section 2A. We'll finish the rest up later.